So the overall theme of this paper or this presentation is how, how some algebraic and combinatorial structures have really saved us when we've been attacking a particular analytic problem. And so I'll be talking about a problem that appears in the context of both the theory of regularity structures, but also in branched rough paths. But I'll focus on the context of branched rough paths and also give a brief overview in case people are not familiar with that theory. So the work I'm sharing is joint work with Timothee Bonnefoi, Augusin Moinat, and Hendrik Weber. So let me begin. So what's the motivation for what I'm talking about here? Well, me and my co-authors wanted to develop a systematic understanding of how we can glue together deterministic arguments from ODEs and PDEs at large scales with the local solution theory for various rough differential equations and SPDEs given by the theory of branched rough paths and the theory of regularity structures. And what we're hoping to accomplish, well, why we want to understand how to glue these two types of analysis is we want to be able to prove global in time and space, so space for SPDs, well-posedness for these equations. So there's been, right at this point, the theory for the local theory for rough differential equations and also SPDEs is fairly mature, but there is a lot less understanding of how to prove global well-posedness. And so recently, we've been looking at equations that have very strong damping terms and trying to prove strong coming down from infinity type bounds. I'll make that a little bit more precise in a following slide, but first, maybe I'll try to give, I'll kind of give us another piece of strong motivation. So one equation that has been studied a lot in the SPDE community is the phi-4 stochastic quantization equation. So here, formally, phi is a function on space-time. And you should think about this term as a rough random driving term. So it's a rough random space-time process. And in the context of stochastic quantization, it would be space-time white noise. So this equation appears as the Markov process associated to the phi-4 quantum field theory. So that's why it's called the phi-4 equation. And it took a long time to develop a local solution theory for, because the presence of an extremely rough driving term means that this equation can't actually be solved in a space of space-time functions. It actually needs to be solved in a space of distributions. So here, phi will actually turn out to be a distribution. And so this led to the need for studying how to renormalize and prove local well-posedness for renormalized SPDEs. So the local theory was the first result on the local theory for the phi-4 equation beyond the regime where you can treat it classically was in the theory of regularity structures in 2014. But work on the global well-posedness took quite a bit more time. So the classical theory completely breaks down when you look at this equation in 3 dimensions, where you take the driving noise to be 3-dimensional space-time white noise. And so this is, again, the Markov process associated to the phi-4-3 Euclidean quantum field theory. And so previous work on a priori bounds and global well-posedness was done by Moinat and Weber, Gubinelli and Hoffmanova, Alberverio and Kusuaka. But a lot of this work was kind of very specifically tailored to 543. And so one problem that we were interested in was how can we kind of generalize this analysis so it's less model specific? So some of what I'll be talking about later in this presentation about the algebraic and combinatorial structures has, for instance, allowed us to treat this equation to get good a priori bounds that allow you to show global well-posedness in the whole subcritical or super renormalizable regime. And so this is difficult because the local solution theory becomes more intricate as this rough driving term becomes more and more singular. So in the language of quantum field theory, we can do stochastic quantization with essentially global well-posedness for phi 4 minus delta. So we can approach the critical dimension from below. So the equation that I'm going to be more focused on is this equation. So it's a rough differential equation with strong damping. So this is this isn't a PDE. This is just essentially a differential equation. And here, y is just a function. It's potentially a vector valued. It goes from time to rk. And then here, the rough driving term is now played by this x. So you should think about x as a vector valued driving noise. And here it's alpha holder, where alpha is positive, but we're going to allow for it to be arbitrarily small. And so the overall structure of the equation is you have this rough driving term that's combined with these sigmas, which we assume to be relatively nice. So if you want the kind of easiest assumptions to think about, you can think about smooth and with bounded derivatives. And then we have, again, this strong damping term. And so the classical theory for dealing with these equations, so without using any sort of technology from rough paths, breaks down as soon as you take alpha equal to 1/2 or lower. So if you want to treat alpha arbitrarily small, then that's going to require formulating this, or one way to go beyond the classical theory to treat this equation is to use the theory of rough paths. There's previous work on this class of equations by Reidel and Schützau. But we were interested, and this is joint work in progress with Timothée, Augustin, and Hendrik, to leverage our SPDE arguments for this differential equation. And our hope is that once we completely understand how to solve this problem to get strong a priori bounds, then we're going to be able to treat the corresponding SPDE. So for instance, so this equation in some sense is easier because it's not a PDE, but it's more complicated because you have a generic nonlinearity versus just the polynomial nonlinearity in this equation. So it's easier in one sense, but more difficult in another. And the hope is if we can combine the insights from both, then we can also treat SPDEs with fairly generic nonlinearities. And of course, the kind of overall goal why we're interested so much in these a priori bounds for SPDE is that if you think about these SPDEs, for instance, this one as the dynamic for some Euclidean field theory, then a priori bounds on the dynamics are actually a crucial ingredient to showing that the dynamics themselves can be used to construct the Euclidean field theory. So for instance, constructing this dynamic and having strong bounds can allow you to construct 543 for essentially any range of couplings in infinite volume. So in some sense, we understand how to do that for the 5-4 equation, but then there are lots of interesting, tantalizing problems related to other models. So for instance, the Sine-Gordon equation or stochastic Yang-Mills. So getting these a priori bounds is also super interesting because it's a crucial step in order to say something about the static models. So to just give a kind of description of the type of bound that we're talking about. So here, the easiest case is when sigma, so I don't want to state the condition because it's a little bit technical, but just assume that sigma has a certain number of derivatives that are all bounded. Then, if you have a solution to this equation on some interval 0, 1, then you have this sort of a priori bound. So basically, you have a bound that does blow up as you approach 0. But the key fact is that it holds uniformly over your choice of initial data. So this term is the blow-up factor as you approach time equals 0, while this one is, I'll describe it later, is basically stochastic data that involves how large this noise is. But for instance, if you have a sort of bound like this, then you can show that the equation, it's fairly easy to show that the equation can't blow up in finite time. And so I'm not going to state it, but there are similar coming down from infinity bounds for the 5-4 equation in the subcritical regime, where you're not looking at a time domain, but you're looking at a space-time domain. All right. Any questions so far? Okay, so I'll continue. So let me just overview the philosophy that is at play in this equation for studying these equations. So again, they're ill-posed on classical spaces. So that's because essentially of the low regularity of the driver makes it impossible to understand how to interpret nonlinearities of the solutions or integrals of the solution on any space that you'd expect this, any classical space that you'd expect the solution to live on. So the key idea in rough paths and the theory of regularity structures, which kind of allows you to go beyond the classical theory, is that you can often construct in practice via stochastic techniques various iterated integrals of the rough driver. So for so in the PDE case, I called it this, but in the rough differential equation case, I just called it X. So you can define via stochastic techniques various iterated integrals of these objects, even when they're not canonically defined. And so, for instance, in the 5-4 theory, it's the construction of these iterated integrals where you'll see the necessary prescription of a divergence renormalization scheme. So I won't be talking about how you renormalize the kind of QFT sort of divergence renormalization story here. So that's kind of hidden inside of the construction of these integrals. But I want to talk more about the solution theory once that's done. And so once you have these monomials, you can construct new spaces of functions and distributions that admit good local approximations in terms of these iterated integrals. So what this does is essentially gives you a novel theory of Taylor expansions. So you can imagine having a notion of Taylor expansion in terms of these iterated integrals. Then you can have a new class of regular functions or distributions where regular means that you're well approximated by one of these Taylor expansions. Okay. So, and so the key fact is that these spaces are in some sense regular since we have Taylor expansions, but that's only in a novel sense. Classically, the objects inside of them can be quite irregular. But this sort of jump in thinking here allows you to pose the equations on these new spaces. So because of this new type of regularity, the equations themselves become well posed, at least locally. And so what's the philosophy for these a priori bounds? I'll just explain the kind of overall analytic idea is that we convolve the entire equation at some scale L. And so you would get something like this. So here subscript L means averaging on some time scale L, which we think of as fairly small. But if you average the entire equation, then you're not going to quite get this nonlinear expression, right? Because averaging doesn't automatically commute with this nonlinearity. And so you'll get a commutator that comes from interchanging the averaging and this damping term here. So now you're looking at an equation, and this equation we're going to analyze just using standard ODE techniques. And so we have a good damping term, so we know how to prove coming down from infinity, but we need to have the ability to control these terms. And it turns out that when you control these terms, especially this commutator, you're going to have to actually use the fact that Y has this novel type of regularity. In particular, you're going to need to use the regularity of certain generalized derivatives of this process. I'll kind of make that more precise on a later slide. But the issue is that unlike in classical spaces, you don't really have the same sorts of hierarchies between the regularities of derivatives, right? So for instance, if I'm, in the classical theory, if I know like if I know that my first derivative is C alpha, then I know that my second derivative is C alpha minus 1. So in this novel situation with this non-classical regularity, you don't have those sorts of relations. All the conditions on various derivatives are actually fairly independent. And so if you just try to write a bound that uses all those generalized derivatives, then you can't close the argument where you're trying to use these ODE principles. So you're stuck. Now the solution is that you can instead use the fact, so if you assume that Y is a solution to the equation, it turns out that there's new relations between these generalized derivatives. And so then these relations are, you see them via using some algebraic combinatorial machinery. So we called it coherence, but I'm sure it goes under many names, but it's, it was seen in past work by Brunet, Shevarev, Price, and Fritz, and also in joint work with Brunet, Shevarev, and Heirer. But the key idea is that by using this algebraic machinery, we're able to find these relations between these generalized derivatives and close our ODE arguments. And so some past work on a priori bounds basically was able to identify these relations by hand, but in our work with my co-authors, we've been interested in trying to make this systematic. So how can we develop machinery that allows us to get all the relations that we need to treat equations any equation that is that can be kind of arbitrarily irregular up to the point where you still have a local solution theory. So, okay, so I wanted to give a quick overview of branched rough paths, which is the formalism that we use to study the equation for y that I introduced earlier. So let capital N be given by this value, where alpha is the Holder exponent for the rough driving noise. And so then I'm going to let T consist of all rooted trees with no more than n nodes, where each node is decorated with by an element of the set 1 through D, right? So each node is decorated by a value that specifies a component of the driving noise. So I've just drawn some examples of these decorated rooted trees. So the fact that they're rooted is important as well. And I use this notation to just indicate the number of nodes in a given tree. Okay, and there's a typo here. This should be the same symbol as this one. So there should be a math-cert T here. But the idea is that these trees index iterated integrals of the rough driving term. So if you just have a single node with an index, then that corresponds to just an increment of your driver, and then the trees correspond to going beyond iterating more. So for instance, here I have a J integral followed by an I integral, and so then these trees can have, in a certain sense, they're branched. So this allows, so we're not working in the setting of geometric rough paths, but for branched rough paths, you can have products appear in the iterated integral as so. And I think there's a typo here. This should also be an I here. Now, one important fact is that while the driving, if you give me the driving noise X, I can immediately construct its increments like this, but the construction of these iterated integrals is not necessarily canonical, right? So these are objects that if X is of really low regularity are not canonically defined, and so are often defined via some sort of stochastic argument. Okay. So going forward, if we define a forest, so I'll define a forest next, which is just a set of trees. So here's an example of a forest F, and it's helpful to think of it as a commutative product of trees. And another important forest is going to be the empty forest, which I'll just indicate with this one. And an important fact is that you can turn a forest into a new tree as follows. So if you give me a forest and then I can turn it into a tree by basically adding a node and then connecting the roots of all the constituent trees to that new node. And here there's a little typo, but this should be, this new node would have decoration mu. So this subscript tells you the decoration to put on your new root. Okay. And so a character that's going to be important for us, which you also saw in Yvonne's talk and which many of you are familiar with, is the Grossman-Larsen coproduct, which for me will just be a linear map that goes from the algebra spanned by forests to the tensor product of the algebra spanned by forests with itself. And so it's the coproduct that's given by admissible cuts. So here, I've kind of I should introduce some dots here because this isn't the whole expression. But the idea is that you sum over all the ways to cut this tree. So you have these two terms, but for instance, what you could do is cut this edge and you'd put the cutting to this side and the tree that's left over on this side, or for instance, you could cut this edge and this edge. And so then you'd be left with this tree and then this tree as cuttings, and then this would be the tree that's left over. And so there are many more terms here that come from all the different ways of doing admissible cuts, which are cuts on edges of the tree where you don't have one cut following another cut. And then this is how you define the coproduct on a tree, but you define it on a forest multiplicatively by just applying it to each of the trees in the forest. Okay. So we call X a branched rough path if for all trees you have the following two facts. So the first is that you have a type of holder bound on your iterated integrals. And so the holder bound is that this evaluated on this tree H between two time points S and T should behave like S minus T or should be bounded above by S minus T raised to the power alpha times the number of nodes in the tree, right? So each node corresponds to an instance of X that's being integrated. And then if you should get an alpha for each of these nodes. So this is the sort of bound that you'd like to enforce. And the second one is an algebraic condition, which is called Chen's relation, which involves this coproduct, but it's basically an increment property for these iterated integrals. Okay, so if we have a way of mapping these trees to iterated integrals that satisfies these conditions, then we call it a branched rough path. Okay, so, oops. So our solution to our equation is actually going to be a controlled rough path. So that's an object in these new spaces that are locally well approximated by these iterated integrals. And how you encode that is it's a map from our time horizon to the vector space spanned by all these trees, along with the empty forest. And so you should think about, again, this as encoding a Taylor expansion for y, where this coefficient is actually the value of y. But in this sum, we are encoding various derivatives of our solution. So you should think about this as sort of being a generalized derivative with respect to a tree. And so on these controlled rough paths, we're going to impose the following regularity property. And so this is the regularity property on derivatives that I indicated, I mentioned earlier. So the regularity property is that if you form this quantity using the operations I described before, so the rough path and then also the coproduct, then this remainder should satisfy this sort of bound. And so what's the meaning of this expression? Well, this is the derivative of y in sort of the h component evaluated at t, and then this quantity should be interpreted as the H derivative of y Taylor expanded with a base point S evaluated at t. So, so this algebraic machinery allows us to basically write out Taylor expansions like this. So for instance, if I put a 1 here, this would just actually be in the Taylor expansion for the actual function evaluated at t, but based at s. And so if I'm taking the derivative evaluated at t and subtracting the Taylor expansion for that derivative based at s evaluated at t, then this is just some sort of Taylor remainder. And so the key ingredient that we need in our analysis is good bounds of this order on our Taylor remainders. But then again, as I said before, there's no real hierarchy between these Taylor remainders. So, so the space of controlled rough paths, that is these sorts of expansions that satisfy this sort of regularity condition, it's a vector space where we can solve the equation as a fixed point problem. But in this vector space, a priori, there are no clear relations telling you that if you have control over one of these remainders, you have control over another. Okay. So what's the key idea? The key idea is that you can show that solutions to the equation actually also satisfy a nonlinear constraint. So it involves this symbol epsilon that you also saw in Yvonne's talk. But basically, if you just look at the fixed point problem in a completely algebraic sense, then the values of these generalized derivatives are actually completely fixed by the value of the solution itself. So the one coefficient. And so that dependence is encoded via a function. So the H derivative is determined by ys. Here it should be a yt, sorry. So it's the same point here. By a function epsilon of h. And this function epsilon of h is generated inductively from the structure of the tree. So if your tree was built by taking this forest and then gluing them together at this node, then what you do to compute epsilon of that tree is you take the appropriate derivative of the sigma that's associated to that component of the noise, and then you multiply by the epsilons of all the trees that were inside the forest. Okay, so all the trees that are above. And so this gives you an inductive procedure. Here I put squiggly equals because there are various combinatorial factors that also appeared in the Yvonne slide. So symmetry factors, but I'm not including them just so things stay clean here. And this symbol didn't appear here. Sorry about that. But the kind of base case of the recursion is that the tree that consists of a single node with decoration mu is just associated to the sigma of mu. Okay, so the base case of the recursion are just the sort of generators of the trees. So just single nodes carrying a decoration. Okay. And so the key new ingredient in our analysis is we define what we call a multiple grafting operation. If in the work with that I referenced by Yvonne, Yvonne and Rosa Price and Ilya Shevrev and Peter Fritz, and also previous joint work with Martin Heirer, Ilya, and Yvonne, we show that these epsilons are prelimorphisms the kind of preely operation is a grafting operation, of grafting one tree onto another. So what we do in this paper is we generalize it to where we graft a forest onto a tree. And here, again, there are lots more terms here, so I should have included ... But the idea is all you do is you find ways to sort of glue this tree on top of this tree. So here, I could glue this one to the root, this one onto this node, and this one onto this node, and I'll get this one. So the red lines indicate the gluing operation. But then another thing I could do is I could actually glue this one instead of to the root to this node to get something like this. And then glue this one to the root to get this one, and then glue this one to this node to get something like this again. And so then you'll get actually many more terms here, not just these two. And so the key property is that with this grafting operation, similarly to grafting single trees, you have a good relation between the epsilons and this grafting procedure. So if you extend this epsilon to a linear map on trees, then it turns out that you get a formula for the epsilon where the generator is just replaced by, oh, sorry, here, this should just be an H. There's some various typos here. So it just becomes the epsilon of H with these Hj. So the sigma U gets replaced by an epsilon of H. And so we can combine this with an adjoint relation, which is not hard, is not so hard to show, which just says that this grafting procedure in some sense is an adjoint for the co-product. But again, I'm putting kind of approximate equalities here because there are all sorts of symmetry factors that go on to make these identities actually true. And so at the end of the day, what we're able to show is that under this coherence condition, the remainder for the H derivative is actually, you can write it itself as a Taylor expansion of the epsilon. And then this Taylor, using this kind of Taylor expansion formula, you get a bound that controls this quantity in terms of the remainder for the one coefficient. So this gives you control over, basically this tells you that if you have control over this quantity, then you have control over all of these generalized derivative remainders. And this allows you to close the ODE argument. And so, so that actually, I think, yeah, finishes my presentation. So yeah, thanks for listening.
Thanks a lot. So let's play Ajay for his talk. Okay, so the floor is open for questions.
I have a question for you, Ajay. Thank you for the nice talk. Just maybe it's I don't know, it's like orthogonal, but you are trying to develop some method to derive some a priori estimates on some dynamics. Usually, you know, have you ever also tried to consider, like, so to apply some generalized change of variable formulas on these dynamics and try to, with some functionals, and try to understand, like, you know, some generalized Ito formula to this solution and try to understand if you can do some, if you have some control of this object. I don't know, it's a...
Oh yeah, it's an interesting question.
So
yeah.
Because that's usually what people do, they know, for energy solution, like that's what people usually take solution, say some Lyapunov functional, let's say something like that.
That's right. Yeah, I mean, I think, yeah, using, I mean, so for more difficult models, like for instance, for something like Yang-Mills, yeah, when you don't have like a super strong damping, then you may want to use some sort of Lyapunov function. So we haven't really, yeah, we haven't really kind of used that sort of thinking with this framework yet, because we just kind of, at this point, we think we kind of really understand completely the strong damping case. And we have some partial results without strong damping, but we haven't started using Lyapunov functions and so on in our analysis.
No, but yeah, of course, Lyapunov functional. Just by the idea, it's like to find some functional and to just contract your dynamics and something like. Because usually there are also these generalized change of variable formulas for this solution and so on. So just to mention, that's maybe if you're interested. Okay.
Any more questions? Comments?
Maybe one question, if I may.
Yes, go ahead.
So in the book of Heyer and Fritz, they also have like a section where they talk about a priori bounds. I was wondering why that, at least if it's not too singular, your rough path, if alpha is big enough, if that would be applicable in your case, or if not, what kind of the difference might be?
Well, yeah, I mean, I think one thing is we want these sorts of, we were interested here in these strong coming down from infinity type bounds. Yeah, I mean, I think we're kind of interested in sort of various, I think, yeah, we're interested in various generalizations that go beyond that. So for instance, we can also, so I didn't say it, but we actually don't need, our kind of formalism actually can go beyond these sigmas being bounded. So our goal is to basically, yeah, I mean, our goal was to basically find a way to sort of glue some very straightforward ODE analysis on larger scales with the rough paths on small scales. It's been a long time since I looked at that in the Fritz Heyer book. But yeah, I mean, I think what we do is a little bit different.
Okay, thank you.
Okay. Any more questions? Comments?
Yes, sorry, I have a question.
Yes, go ahead.
Maybe a bit naive, but so how do you determine the number of edges that are attached to your vertices? I thought it was determined by the degree of your interaction. So if it's phi3, if phi3 in your equation, then you have 3 edges attached each time.
That's right. So that's a good question. So if you're treating, sorry, let me go back to the, if you were treating an equation like this, then you would have at most 3 descendants of each node. When you're treating an equation like this, one important thing that I didn't really specify is how this equation is actually formulated on these controlled rough paths. And basically you lift this generic nonlinearity via Taylor expansion.
Okay.
So then you see interactions of all sorts of different orders.
Okay, thanks.